This video is going to be about rotational kinematics, and I am currently on hall duty, so if you hear random noises or random conversations, that is why. Okay, so first thing first is, what is rotational kinematics? So far this year, we have looked at things moving in straight lines for the most part, right? They're moving forwards or backwards, but that's not the only way things can move. Things can also rotate, so that might be like a turntable that's rotating, or it could be a ball that is rolling across the surface. Okay? So rotation on its own would be just a turntable, and then the ball rolling would be rotational motion and what's called translational or linear motion. What's important to keep in mind with regards to rotational kinematics and really all rotational topics is that they're not really new topics. It's rather a different way of looking at old topics. So rotational kinematics is just a new way of looking at kinematics, but for rotating objects. Okay, so first thing I want to do is look at our linear variables for kinematics and compare them to our rotational variables. It would be good if I could spell variable correctly. Okay, so first thing we talk about in linear motion with kinematics is position or change in position. So for an object that's rotating, we talk about a change in angular position. So we use theta. Okay, now theta is measured in radians. Okay, so that's essentially how far an object rotates in a given amount of time. Okay, so one rotation is considered to be 2 pi radians. Okay, now we can actually convert that rotational motion or that rotational distance into a linear distance, and we can convert linear distances into rotational distances. Okay, so any linear distance is going to be the angular distance times the radius of the rotation. Okay, so then let me label this conversion. Okay, so then so I can prove to you that this equation works, because if an object makes one rotation, the linear distance traveled should be equal to the circumference. So in one rotation, the object travels 2 pi times r. Well, that is in fact the circumference, so this equation does work. Sorry for that aside. Okay. So next, in linear motion, we talk about velocity, right? Velocity is measured in meters a second usually. So in rotational variables, we talk about angular velocity, which is represented with the Greek letter omega. It's a lowercase Greek letter and kind of looks like a fancy W. Okay, so this is measured in radians per second. So again, we can convert between angular velocity and regular velocity. Regular velocity is the angular velocity times the radius. Okay, maybe you're seeing a trend by now. Okay. Then the last thing we talk about in kinematics is acceleration, which is measured in meters a second squared. Okay. So in rotational variables, we talk about angular acceleration, which is the Greek letter alpha, measured in radians a second squared. Okay. Our linear acceleration, or tangential acceleration as it's called, is just the angular acceleration times the radius. Okay. Now these variables are not necessarily on your reference table, and these equations are not on your reference table, so you do need to remember those. Okay. So we can use this kind of idea to help us figure out what our kinematics equations for rotation are going to look like. So in linear motion, we have the position versus time equation, which is x equals x0 plus v0 t plus 1/2 a t squared. So in rotational motion, that's going to become theta, our final angular position equals theta 0, our initial angular position, plus omega 0 t, so our initial angular velocity, times time, plus 1/2 alpha t squared, where alpha is our angular acceleration. Okay, so I've basically taken the linear equation and replaced it with all of my rotational variables. This equation and all of the other kinematics equations for rotation are not on your reference table, but they sort of are because they're kind of hidden in the linear stuff. So the other equation we have is v equals v0 plus at. So for rotation, that can become omega equals omega 0 plus alpha t. And then we have v squared is v0 squared plus a 2a change in x. So that becomes omega squared is omega 0 squared plus 2 alpha delta theta. Okay. So same equations, and we approach the problem solving the same way. So let's say we have an object, a turntable, right? It starts at rest, has an angular acceleration of 2 radians a second squared, and we are accelerating for 3 seconds. Okay. Well, if I start at rest, that means my initial velocity is 0. Angular acceleration is 2 radians a second squared, and I accelerate for 3 seconds. So let's say the first thing I want to know is what angular position has the turntable rotated through. So I'm looking for my change in theta. So if it's confusing to think about these variables as angular variables, just write them as your linear variables. So v0a t, change in x. The only equation that has those 4 variables is my position versus time equation. X equals x0, v0t, plus 1/2 at squared, which rewritten for rotational variables is theta 0 plus omega 0 t plus 1/2 alpha t squared. I can assume my initial angular position is 0. Because I start at rest, my initial angular velocity is 0. So I have my final angular position is 1/2 angular acceleration times time squared. So I'm looking for theta 1/2 2 radians a second squared times 3 seconds squared. And that gives me 9 radians as an angular displacement. Okay. I could also use this to find my final angular velocity, okay, which would just be v. So I could use v equals v0 plus alpha t. v0, or rather omega equals omega 0. This was an a, oops, plus alpha t. So this initial velocity is 0. I'm looking for final velocity. Alpha is 2 radians a second squared. I'm moving or rotating for 3 seconds, so my final angular velocity is 6 radians per second. Okay. Now, just like with linear kinematics, we can look at graphs for angular kinematics. So instead of position versus time, we look at angular position versus time. So for the example given, we start at 0 and end at 9. We're accelerating in the positive direction and rotating in the positive direction. So my graph would look like that. Exactly the same as a position versus time graph would look like for an object speeding up. Velocity versus time would be similar. I'd start at 0 and end at 6 with a nice straight line. Now, I did mention rotating in the positive direction versus rotating in the negative direction, but didn't actually say what's positive, what's negative. So for rotation, the positive direction is considered the counterclockwise direction. Okay, and that comes from math class. So if we think about x, y, right, we usually say the x-axis is 0, and then we measure our angles counterclockwise from there. Okay, so that's why we say the positive direction is considered counterclockwise rotation. The negative direction is clockwise rotation. Okay. So again, we can approach these problems as if they are kinematics problems. Everything that we learned in kinematics still holds true for rotation, just different variables. Okay? Positive is counterclockwise, negative is clockwise. So let's think about another example. Let's say I'm presented with a graph, right? And this is a position versus time graph. I'm told that this initial position, let's say, is 4 pi, and this final position here is -10. Okay, let's say I'm also told this object starts at rest. Okay, and this occurs at 8 seconds. Okay. So looking at the graph, it looks like this graph is going to speed up as time goes on. So this object has an acceleration in the same direction as its velocity. My slope is negative, so that means the acceleration is negative. Okay. So my initial position, or theta 0, is 4 pi. Actually, let's make that a little bit nicer of a number. Let's just make it 4. 4 radians. My final position is -10 radians. My initial velocity is 0, and I have a time of 8 seconds. So let's say the first thing I want to find is the angular acceleration. So again, we can think of these in terms of linear variables. So I have x0, x, v0, t, and a. So the only equation that has those is the position versus time equation, which written in terms of rotational variables is theta equals theta 0 plus omega 0 t plus 1/2 alpha t squared. So theta final is 10 radians. Theta initial is 4 radians. Initial angular velocity is 0. I'm looking for alpha, and the time is 8 seconds. And I got to remember to square that. So I'm going to subtract 4, so I get -14 is 1/2 alpha times 64. Okay. Then I multiply both sides by 2, so I get -28 is alpha 64. And my angular acceleration ends up being -28 over 64, whatever that simplifies to. And again, it makes sense that it is negative because the object is moving in the negative direction. We could also use this to find the final angular velocity, omega, or in terms of linear v. We kind of can use whatever equation we want at this point. I'm going to use omega equals omega 0 plus alpha t. So initial angular velocity is 0. Alpha is -28 over 64 radians a second squared. My time is 8 seconds. So this can simplify to 8, and my final angular velocity is -28 over 8 radians per second, and that makes sense because this slope here is a negative value, and it is larger than 0. Okay. So again, rotational kinematics is just linear kinematics with different variables. Okay. We'll talk more about these conversions and how they get useful as we move through the different units. Okay. But know that all of these variables represent tangential. So if we want to find our tangential distance, our tangential velocity, or our tangential accelerations, we would use these equations here. Okay? So at any point on the disk or on a rotating object, the tangential values are based on where the actual object, or where the object, what point on the object we're looking at. Okay? Whereas the angular objects are all the same. So I'm going to write that out. So the angular values are the same everywhere on a rotating object. But the linear values, so linear, whereas they're called tangential values, depend on r, or how far you are. Okay? So if we have an object here that is rotating counterclockwise, okay, and any given point in time, the angular displacement of A is going to be equal to the angular displacement of B, but the tangential or linear displacement of A is going to be larger than the linear displacement of B, because A is at a larger distance from center. The angular velocity of A, because the angular displacements are the same, is going to be the same as the angular velocity of B, but the tangential velocity of A is always going to be greater than the tangential velocity of B, because A is farther out. We have a larger distance to travel in the same amount of time. Okay? Angular acceleration of A is always going to be equal to the angular acceleration of B, but the tangential acceleration, so the acceleration tangent to point A or tangent to point B, okay, is going to be larger than the tangential acceleration at B. So again, all of the angular values are always the same. Linear values depends on the radius. And that is about it. I think I'm actually done. I've acted like I was done for like 5 different times. That's it. Bye-bye.
Like this weekend, I hope to accomplish these 2 things.